Hello again, and welcome to Advanced Physics for High School Students. This is Lesson 64, and it is entitled Fluid Pressure, Weight, Density, Pressure, and Pascal's Principle. I'll start by acknowledging Walter Leuven of the Massachusetts Institute of Technology for much of the content and presentation in this lesson. The link that's here will take you to his 50-minute long lecture given at MIT, in which he talks about a lot of today's topics. And I have borrowed directly and pretty freely from his words and diagrams. At the end of this lesson, I'll take you to a 2-minute video clip showing Walter Leuven in action. For the moment, let's forget about gravity. We'll add it back later when we need it. Let me take a closed compartment that's filled with a fluid. There's a piston on top, and there's a fluid that's inside. It could be a gas or liquid. For right now, it doesn't matter. And now let me apply a force up here. This piston on top has an area A, and we define the pressure to be the force divided by the area. And it has units of newtons per square meter, which we call a Pascal. 1 Pascal is equal to 1 Newton per square meter. Now, in the absence of gravity, the pressure is the same everywhere in this vessel, and that's what we call Pascal's principle. Pascal's principle says that the pressure applied to an enclosed fluid is transmitted undiminished to every point in the fluid and to the walls of the container. Keep in mind that pressure is a scalar. It has no direction, but force has a direction, and the force exerted by the fluid on anything, and therefore also on the wall, must everywhere be perpendicular to the wall, because if there is any tangential component, then the fluid would start to move. And for this lesson, we're focusing on fluids at rest. That's called hydrostatics, the hydro meaning water and statics meaning at rest. So if I take any element, and I'm going to take an element that's right here, and I call that little element of area delta A, then there's a force that's acting on it, and that force we'll call delta F, and it is perpendicular to the wall. So now, if I take the ratio of delta F to delta A, in the limit of making delta A very, very small, as delta A goes to 0, then that must be the pressure, the same pressure that I'm applying to the top of the piston. Now this has some amazing consequences, which are by no means so intuitive. This is the idea of a hydraulic jack. So I have here a very peculiar shaped vessel. Over on this side I have a small side, and over here on the other side I have a large side, and on this side I have a piston which I'll call A1, and on the other side I have a piston which I'll call area A2, and everywhere inside there's a fluid which fills this container. Perhaps it's hydraulic oil. That's what's usually in hydraulic jacks, some sort of oil. And now on the left side I apply a force which I call F1, and on the right side I apply a force which I call F2. And so on the left side I apply a pressure F1 divided by A1. So according to Pascal, everywhere in the fluid that pressure must be the same. So now I just assume that the effect of gravity is absent, and I'll discuss that shortly, but it doesn't really change this situation very significantly. So the pressure then will everywhere be the same throughout this fluid. The pressure due to the left side is F1 over A1, and on the right side it will be F2 over A2. Now let's just suppose for a moment that A2 over A1 is equal to 100. What that means is that this force on the left side, F1, could be 100 times less than that on F2. In other words, I could put on the left side a weight of 10 kilograms, and on the right side, on A2, I could put 1,000 kilograms, and it would be completely in equilibrium. That's not so intuitive. This is used all the time in garages. What they do is this. They put on top of this large piston an automobile, and someone pushes on the left side A1, and then on the right side A2 where the car is, it goes up. And so your first thought may be, gee, isn't that a violation of conservation of energy? Am I not getting something for nothing? Well, not really. Suppose I push this left side down over a distance of d1. That fluid that's displaced ends up over here on the right side, and the right side goes up by a distance of d2. But that same amount of fluid that leaves the left side here at A1 will end up over on the right side at A2. In other words, A1 times D1, which is the volume of fluid that leaves the left side, is equal to A2 times D2. Now if the force on the left side is 100 times less than the force is on the right side, then that means that the distance that the right side moves, D2, is going to be 100 times less than the distance that the piston on the left side moves, D1. And if we look at the work that's involved, the work on the left side is F1 times D1, and the work on the right side is F2 times D2. Well, if F1 is 1/100th of F2 and D2 is 1/100th of F1, then I haven't violated conservation of energy at all. So the work I do when I push the left side down, I get back in terms of gravitational potential energy by lifting the car. So if I wanted to move the car up by 1 meter, and if the ratio of the areas is 100 to 1, I would have to move the left side down by 100 meters, and that might be a little impractical. So these hydraulic jacks are designed in such a way that you can pump the handle on the left side repeatedly, and every time you cycle the handle, the liquid flows back in again to the left side of the jack. But indeed, you have to effectively pump 100 meters for the car to go up by 1 meter if the ratio of the areas is 100 to 1. That's why you have to jack and jack and jack in order to get the car up. Let's do an example problem here. The example problem is 64.3. It's a little out of order, but we'll do it anyway. The pressure produced by the force F1 on the frictionless piston with a cross-sectional area A1 is transmitted through the perfect fluid. Find the resulting force F2 on the piston with area A2. And in the diagram they give us F1 is 75, A1 is 10 square centimeters, F2 is what we're looking for, A2 is 80 square centimeters. Pascal tells us that P1 is equal to P2, and on the left side P1 is F1 over A1, and on the right side P2 is F2 over A2. And now I'm trying to find F2, so solve that equation for F2. So on the right side, I would be able to exert a force of 600 newtons. I would like to take you to a video showing a group of students in a shop class building and assembling a hydraulic jack. These blueprints show you the pieces that they have machined out of probably aluminum, I would say, to build this hydraulic jack. So this fellow now is assembling the large piston side of the jack, the equivalent of the right side. That paper that's there is a gasket that's going to seal the hydraulic oil in that side of the system. And these support rods that are being assembled there are going to hold the assembly, the large piston assembly, on the right-hand side of this jack. Now he's taking the tube that's going to hold the piston and putting it in place, and he's setting that onto these supports. And he's inserting now the large piston, the large area piston, and the rod that's going to jack up the large weight that would be supported there. And he's putting that together now and securing it with the appropriate fasteners. Now he turns to the small piston side, and in the small piston side he is putting together the assembly that's going to hold the small piston. There's the small piston itself. He's sealing it so that it's got some liquid on it, and he has some appropriate supports there. And now he's going to take and put a handle that will be used to help hold the thing together. This part he is assembling the place where the small piston and the large piston come together. And so there's going to be a seal between the small piston chamber and the large piston chamber. Now he's putting in the part that allows oil to leave the large chamber and go back to the small chamber when he wants to remove the jack. And now the handle assembly is going on. Now he's going to fill the jack with hydraulic oil. So hydraulic oil is going into the large chamber side, and now it's going into the small chamber side. When the jack is full of oil, the jack is assembled, and now he's pushing the left side and the right side rises, and he essentially has himself a machine that's able to do this using Pascal's principle. And now you see the class that has done the project. Now let's add gravity back in. Of course, gravity has an effect on the pressure of the fluid. If you go down into water, you know that the pressure goes up. You feel this every time you dive into the deep end of the swimming pool. You can feel it on your ears as you go deeper and deeper. And I would like to derive an expression for the pressure increase as I go down. So I'm going to let down be the direction of increasing depth. And I can choose any shape I want for my liquid. So I'm going to choose a nice rectangular slab. This slab has a height that I'm going to call h, and it has an area on top that I'm going to call A. Of course, the area on the bottom is also going to be A. The pressure here on the top I'll call P1, and the pressure that's down on the bottom I'll call P2. This liquid has some density that I'm going to call rho. And so this rectangular block is going to have a mass of rho times V, which is going to be rho times the area times the height. That's the mass of the block of fluid. There's pressure all around on all sides of the fluid, but the pressure that's on the vertical sides cancel each other out because they're in opposite directions if the fluid's in equilibrium. And now the fluid is in equilibrium, so the upward pressure must balance the downward pressure. So the upward forces must balance the downward forces. Well, now the weight of this fluid is equal to m times g. There's some force F2 that's supporting essentially the bottom of the fluid, and there's some force that's F1 that's acting down on the top of the fluid. Well, Newton's second law says that the upward forces must balance the downward forces, so F2 must be equal to mg plus F1. Now, if the pressure is equal to the force divided by the area, then that must mean that the force is equal to the pressure times the area. The pressure on the bottom is going to be F2 times A. The weight of the fluid is the mass, which is rho times A times H, plus times G, because it's the weight, plus the pressure from the top. Maybe that's atmospheric pressure, the pressure from the air that's on the top of the surface of the fluid, which is going to be P1 times A. Now, I have a bunch of A's there that can cancel. And when I do, I end up with an expression that tells me the pressure at the bottom, P2, is equal to rho times H times G plus P1. And that is an important equation. It tells me the pressure at some depth, H, if I know what the pressure is at the surface of the fluid and what the density of the fluid is as well as the depth. We call this term rho GH or rho HG, the hydrostatic pressure. Sometimes it's called the fluid pressure. Sometimes it's also referred to as the gauge pressure. So when you go to fill your air in your tires at the service station, then that would be the pressure that's inside the tire. The pressure at the bottom we'll call the absolute pressure, and the pressure at the top we'll call atmospheric pressure. So this fluid pressure is due to gravity. If there's no gravity, there's no hydrostatic pressure. We're going to be working mostly with liquids, and most liquids are practically incompressible. It's possible to compress a gas, but it's really difficult to compress a liquid. And so from this point onward, we'll say that our ideal fluid has a density that's everywhere the same. Now, this equation for the absolute pressure has some bizarre consequences. Suppose I had a vessel that I filled with a liquid that has a rather strange shape. So I fill this vessel with liquid, and it'll be filled to this height over here on the other side. And let's measure down to the bottom of the vessel at a depth h below the surface of the liquid.